Today, my presentation is about statically indeterminate problems. Okay, so actually there are two types of problems that occurs in engineering applications. We have the so-called statically determinate problems as well as the statically indeterminate problems. Now, if the equilibrium equation are those equations that defines the state of equilibrium of an object. For example, the summation of forces along the x directions, the summation of forces along the y directions, as well as the summation of moments. So those are the equilibrium equations. Now, if the available equilibrium equations are sufficient to calculate all forces, including support reactions that act on a body, these forces are said to be statically determinate. Okay? In other words, um, the number of unknown force is always equal to the number of independent equilibrium equations. Now, most of the problems that appears during the studies of rigid bodies, those are all examples of statically determinate. If you can remember, you are able to solve such problem by using only equilibrium equations and nothing more. So you solve the problem by using summation of forces in the x direction, using forces along the y direction, and if those are not enough, then you make use of summation of moments. Okay, so the largest number of unknowns usually are two unknowns. Okay, now if the number of the unknown forces exceeds the number of independent equilibrium equations, the problem is said to be statically indeterminate. Okay, so the word indeterminate comes from the condition wherein you will not be able to solve such problems if you'll be only relying to the equilibrium equations. Equilibrium equations are not enough to solve such problems. Okay, but a statically indeterminate problem has what we call geometric restrictions imposed on its deformation. Okay, so from here, from these geometric restrictions, we can look for relationships between the deformations of several points, which can help us generate additional equation. And these additional equations, no, is known as the compatibility equations. So together with the equilibrium equations, okay, plus these compatibility equations, you will now be able to solve statically indeterminate problems. Now, the source of compatibility equations is deformations. Okay, and so that our formula will be valid, the stress should be within the Hooke's law. And Hooke's law expresses the deformation in terms of stresses of force. The equations of equilibrium and compatibility can then be solved for the known process, and we call this one as the force displacement equation. So I have here a very simple example of a situation wherein you have a statically indeterminate system. As you can see from the figure, a bar weighing 7,200 pounds is supported on 3 points. We have support 1, 2 supports 1, and then 1 support 2 at the middle. Let's assume that these supports have different, say for example, cross-sectional area and a different material. Okay, so we cannot assume that the weight will be evenly distributed to these three supports. Okay, so it's not safe to do that. So in other words, we do not know the exact distribution of the weight between the two types of support. Definitely, support one will have a value that is equal for its supports, but support two will have a different value. So we do not know what is the distribution. We don't know how is 7,200 is being distributed to the types of support, although we have three, but uh, the two supports are equal. Okay, so applying now the equilibrium equations. Okay, so we have your weight being directed downwards and the forces F1 uh, represents the reaction of support 1 and F2 represents the reaction at support 2. So by looking at the pre-by diagram, we can say that the weight, which is equivalent to 7,200, is equal to F1, since we have 2 support 1 and plus F2. So what you can see, we have unknowns F1 and F2, yet there is only one available equations that we can use, which is the summation of the forces along the y-axis. So by the law of algebra, you cannot solve a problem wherein you have greater number of unknowns than the available equation. Okay, so this is a example of a statically indeterminate problem. So we have here the procedure for solving statically indeterminate problems. Number one, just like any problems in mechanics, no, it is very important to have or to draw the required free body diagrams, because from there we can derive the equations of equilibrium. It's very difficult to write the equations without referring to the diagram. And then the second step is derive the compatibility equations. To visualize the instructions on the formation, it is often helpful to do a sketch that exaggerates the magnitudes of the deformations. Although in reality, deformations are very small, that it's very difficult to see, so you have to draw an exaggerated sketch for you to be able to see the deformations. And you will now be able to determine the relationships of the deformations. Then after that, you already have equations from equilibrium and compatibility equations, so you will now have enough equations. You will now use Hooke's law to express the deformations or strains in the compatibility equations in terms of forces or stresses. Then finally, solve the equilibrium and compatibility equations for the known forces. Okay, so let's come now to our problem one. The concrete post in the figure is reinforced actually with four symmetrically placed steel bars, each of cross-sectional area of 900 square millimeters. The area of each bar is equivalent to 900 square millimeters. So we are required to compute the stress in its material when 1000 kilonewton axial load is applied. The moduli of elasticity are 200 gigapascal for steel and 14 gigapascal for concrete. So already on our MATCAD worksheet. Okay, so let's define the given. Okay, so we're given with the dimension of the post. Actually, it's the width of the post. Let's say that it's represented by variable b. Okay, your p is equivalent to 300 millimeters. What else? We're also given with the area of the load. The load, let's say that is represented by P. Our load being equivalent to 1000 kilonewton. We're also given with the bar, area of bar, and let's call that one as A sub B. So the area of bar is equivalent to 900 square millimeters. Okay, so we're also given with the moduli elasticity of the two materials. We have for the concrete, and equivalent to 14 gigapascal. And we also have for the steel, we're given with 200 gigapascal. So let's now solve the problem. Okay. So let's recall now the steps in solving statically indeterminate problems. So the first problem is to determine the equilibrium equations. But to do that, you need to have the free body diagram. It is a must. Okay, not only for this type of problems, but for all problems in engineering, you need to have the free diagram, especially in mechanics. So I already have a prepared BD here. So I'll just insert it. Okay. So this BD is actually um, extracted from the total figure by passing a cutting plane through the section of the column, so that the internal forces will be exposed. As in the case now of the concrete and your steel. Okay. So from the figure, okay, we have your PCO. Your PCO is actually the reaction. That's the reaction of your PCO is actually the reaction of the concrete, and your PST is actually the reaction of the steel. So applying now the equations of equilibrium, so the only available equation is the summation of forces along the y-axis. Okay. So let's do the summation of forces. Okay, so we have summation of forces along the y-axis. equivalent to, say, PCO plus PST. And minus the 1000 kilonewton load. And then, since it's in equilibrium, that's equivalent now to 0. Okay? So now our equation would be, we have 0 equals to PCO plus PST and minus 1000 kilonewton. So let's rewrite the formula. We have now 1000 kilonewton up to PCO plus your PST. Okay, so that is our equation. But we can still further simplify this equation. So it's better to express your equations, no, in terms of stress. So we have here PCO, this in terms of force, and PST in terms of force, but the final requirement is the stresses for both materials. So it's better to express these forces in terms of stress. Okay, so we have now 1000 kilonewton equivalent to, so we know that force is equivalent to the stress times the area. Okay, so we have here, let's say, sigma C is the stress at the concrete times A sub C, the area of your concrete. And then plus, we have here sigma S, that's the stress for the steel, times AS being the stress, or the area of the steel. So the next step is to solve for AC and AS. So let's solve for AC, but before we can solve AC, we need to solve your gross area. Your AG, the gross area. So first the gross area, AG. So AG is equivalent to B squared, B times B. Okay, we have 900, I mean 90,000 square millimeters. Let's solve for the steel area, or the area of steel. Since we have 4 bars, and our area of steel is equivalent to 4 times the area of bar, give us 3,600 square millimeters. And finally, we can solve now the area of the concrete. Let's say we have A sub C. So area of concrete now is equivalent to A sub C, equivalent to the gross area minus area of steel. Let's compute the area of your concrete, which is now equivalent to 86,400 square millimeter. Okay, so okay, let's further simplify this equation. So we need just to copy and paste it here. So we need now tools. substitute the value. So we can substitute the value in this. So we just need to combine the 14. Yeah. So that will be our final equation for equation 1. So our equation 1 now is given by 1000 En equals to 6,400 times the stress in the concrete of course linear plus okay. So we already have our first equation. So this is the equation from the equilibrium condition. This is our equation 1. Okay, so we're done with the equilibrium equation. Next, we need to determine the compatibility equation. Okay, so how do we determine the compatibility equation? So let us observe the diagram. We go back to the problem and what you can see, there is a bearing plate on top of the post. The purpose of that bearing plate is to make sure that the stress distribution, the 1000 kilonewton force is evenly distributed between the two materials, that is for your concrete and for your steel. Okay. Now, since the stress is evenly distributed, or the forces is evenly distributed between the two materials, then it's safe to assume that the deformation of the concrete and the deformation of steel will be equal. Okay, so we are compressed by the 1000 kilonewton. They will deform an equal amount. Okay, together they are being compressed by the 1000 kilonewton. Okay, so the deformation should be equal. So we can say now that, let's say this is the deformation of the concrete. Okay, let's present that one as the deformation in the concrete section. Delta C, and we also have here your delta S being the deformation in the steel section. The steel section. And then earlier we conclude that the deformation should be equal. So they are equal. So this is our compatibility equation. Okay, so it's very clear that the deformations would be equal. Let's try to uh, look at the diagram. Okay, so this information, so looks like the equations from the equilibrium will also express the deformations in terms of the stress. Okay, so if you express this one, in terms of stress by using the formula stress times the length divided by the modulus of elasticity. So for concrete, we have sigma c for concrete. That's the length of your concrete section divided by the modulus of elasticity for concrete. Okay, then this is equivalent to, let's say sigma s, the stress in the steel times the length of the steel divided by the modulus of elasticity for steel. And for the figure, it's obvious that the length of your concrete and your steel are equal. So we just copy this one. So the equation will be reduced to, let's cancel x since they are equal. So now we're going to express the strain of a particular material with respect to the other material. So in this case, since steel is greater than the stress in the steel is greater than the stress in the concrete, it is more convenient to express the stress in steel in terms of concrete. Right here. Okay, so the stress now of the steel would be equal to, okay, so the stress of the concrete times the modulus of elasticity for steel divided by the modulus of elasticity for concrete. Okay, and let us substitute the values. Let's combine. Okay, so we have here now the simplified equation. We have stress in the steel is now equals to 100 times stress of concrete divided by 7. So that is the relationship between the stress of the steel and your concrete. This is our equation from compatibility, and this is our equation 2. Okay, now it's the time to combine the two equations. Let us go and copy our equation 1. Okay. And then going to substitute our stress for steel in terms now of the concrete. So we have 1000 GN equals to 6400 times the stress of the concrete. Of course, don't forget the unit, plus 3600 this time. We're going to use this value times 100 times stress in the concrete divided by 7. So this is now the stress of the steel. Of course, don't forget the unit. So our combined equation has only single variable, which is the stress of the concrete. And it's now possible to solve the stress of the concrete. Okay, so we can now compute the value of the concrete. See, this is the concrete. Okay, so that gives us 35 kilonewton divided by 4824 square millimeter. So we need to simplify our answer. Okay, now so the stress in the concrete is equivalent to 35 kilonewton divided by 4824 mm squared. So that will give us now a much clearer answer. So that is 725,5389.718 Pascal, or we can have it in megapascal. So we have the 7.255 megapascal stress for the concrete. Having obtained the stress in the concrete, it's now easy for us to solve the stress in the steel by simply using equation 2. So equation 2 is, okay, the stress in the steel is equivalent to 100 times the stress in the concrete divided by 7. Let's solve this one. Combine. Okay, so we have 103.648 megapascal. Okay, so let's further simplify this one. Okay, so there you have it. Now the stress for concrete is 7.255 MPa and the stress for steel is 103.648 megapascal. Now to problem number 2. The figure shows a rigid bar that is supported by a peanut A and two rods. One made of steel and the other is made up of roots. So neglecting the weight of the bar, this one, we need to compute the stress in its rod caused by the 50 kilonewton applied at the end. Okay, so we have here the properties of steel. We have the area, divided by 600 millimeters, and its modulus of elasticity is 200 gigapascal. And for bronze, we have a cross-sectional area of 300 square millimeters and 83 gigapascal for its modulus of elasticity. So we're already in our MATCAD worksheet. Let's now solve problem number 2. So if you are using MATCAD, your first step is to define the given. So let's start with steel. Let's say area of steel represented by the AST. Okay? And from the table, the value of AST is given to be 600 mm squared. And the modulus of elasticity of steel, let's call that one as E sub st, E sub st is equal to 200 gigapascal, and followed by the properties of the brooms. Let's say area of brooms. Let's represent that one by ABR, and our brooms is given to be 300 mm squared, while the modulus of elasticity for brooms, let's call that one as EBR, or EBR is equivalent to 83 gigapascal. 83 gigapascal. Okay, so the next step now is to write the equilibrium equation. Of course, we need to have a free diagram. So we're going to consider this bar as the body for our diagram. Okay, so I have here now the 3-pi diagram of the bar, and we have here the external forces applied at the bar. Since at A we have a pin connection, so we have here two reactions, AY and AX. Then, since this bar is being acted by a 50 kilonewton downward force and the rods are supporting this bar, so the rods are in tension, so your steel is in tension as well as your brooms is also in tension. Okay, so now we're going to write the equation, but in doing so, we need first to identify what forces are needed in the solution, because not all of these forces will be used in solving the problem. Okay, so we need to ask ourselves what forces do we need and which forces uh, will not be included. Okay, so since we're after with the forces or the stress in the rods, okay, obviously we need PSP and PBR as well as the 50 kilonewton, but we don't need the reactions at the pin. So therefore, we can eliminate AY and AX from the solution. So the logical choice is by selecting A as your central moment. Okay, so we will perform a summation moment about A. Okay, so let's have summation of moment about A. Okay, so let's drag it here so that we can have the larger space. Equals, let's say clockwise movement will produce a positive, and then counterclockwise movement will have a negative sign. Okay, so our PST will produce a counterclockwise movement, therefore this will be negative, so we have 0.6 meters times PST Also our broods, this will produce also a negative, okay, minus 1.6 meters times the fronts, the force in the fronts, and then finally your 50 kilonewton will produce a clockwise moment. Okay, so we have the total length 0.61 and 8. The total is 2.4 meters plus 2.4 meters times 50 kilonewton load. Okay. So since it's equilibrium, this will be equivalent to 0. Okay, so this is equivalent now to 0. So we can copy this. Okay, so this now is 0. Okay, so this should be our equation 1. But since we're after with the stresses in the steel rods as well as in the bronze rod, it's better for us to express the forces in terms of the stress. And force is equivalent to stress times the area. So we can rewrite the equation to be 0 is equals to negative zero point 0.6 meters times the stress in the steel times the area of steel minus 1.6 meters times the stress in the bronze and times area of bronze plus 2.4 meters times 50 kN. So we have now the first equation. So further, we need to combine this one. So let's combine this one. Okay, so that we can have a shorter equation. So we have now, so let's write this one 0. The equation now is equivalent to 1200 meters times Kn minus 360 times stress of the steel. Yeah, let us rewrite now the equation. So we can have 0.6 meters PST as 1.6 meters times PBR is equals to 2.4 meters times 50 kN. Okay. So let's simplify the equation. Okay, so we have now this equation 0.6 meters times PST times the unit plus 1.6 meters. Then equals to 120 meters times kilonewton. Let's further simplify this one by replacing forces in terms of stress and area. 1.6 times stress in steel times area times the unit, and plus 1.6 times stress in the bronze times area of bronze first the unit, and equals to 120 meters times kn. Okay, and then since we also have the value of the area, we can further simplify this one. Okay, so just continue this one. So now the equation is equivalent now to 360 times ST Sm times mm squared plus 480 times stress in the rooms times n times mm squared equals to 120 meters times kn. Okay, so there you have it, our equation 1. So this is our equation 1. Okay, so yeah, we have determined our equilibrium equation. Next, we will determine our compatibility equation. Okay, so let's go back to our figure. Since this is a pin connection, when subjected to a critical load, this will rotate. Okay, so this will rotate in this manner. Okay, so I have already the sketch showing the deformation, the rotation of the bar. Okay, so because of the critical Newton at the end, the straight bar will now be inclined, and your steel will elongate by this amount, as well as your bronze will elongate by this amount. Okay, so from the figure, we can easily determine the relationship between the deformation of the steel and the deformation of the bronze. Okay, since they form a triangle, so we can use the principle of similar triangle. Okay, so now the deformation in the steel is 2.6 meters equals to The deformation in the bronze rod is to 1.6 meter. Okay, so that is our relationship between the two. And let us express this one in terms of the stress. Uh, so we have the stress in the steel times area of steel. And by the way, we need also to define the length. We, we did not define the length. So LST, the length of your steel, is equivalent to, so back to the problem, 1 meter and for bronze is 2 meters. That is 1 meter, while for the bronze, this is equivalent to 2 meters. Let's simplify our equation. So I think it's better to express the length of steel, the deformation of steel in terms of the deformations of the bronze. So we have here steel now equivalent to uh, 0.6 meters times the deformation in the bronze divided by 1.6 meters. Then let us express this in terms of the stress. If possible, if we can simplify this one, okay. So we have this new relationship. Steel is equivalent to 0.375 the deformation of the bronze. Okay, so from here, let's express steel in terms of the stress. Stress T times the length of the steel divided by the modulus RCCT for steel and equals 0.375 times the stress of the bronze times the length of the bronze divided by modulus RCCT of the bronze. Okay, so if we can combine this one, okay, so it's better if we combine that later on. So we have now the stress for steel is now equals to 8.375 stress the bronze times length the bronze force multiplied by the modulo subsisting for steel divided by Okay, elasticity of the bronze and the length and the steel. Let us combine. Okay, so this there you have it, the relationship now. So stress in the steel is now equivalent to, okay, 1.807 to the stress in the bronze. Okay. So we have now our equation 2. Okay. So having determined equation 1, equation 2, we can now combine the two equations. Okay. So our equation 1, and then let's substitute the value of steel, the red steel. Okay, so let's replace this one by this value, the steel. One, 1.8072 times the stress in the bronze. So we only have one unknown, therefore we can solve our unknown. Solve the stress in the bronze. So we have this value. Let's see. So the stress in the bronze is equivalent to 0.1061 kilonewton divided by mm squared. So let's simplify now. The stress in the bronze is equivalent to 106.1 megapascal. Okay, and to solve for your stress in the steel rod, all you have to do is to use equation 2. Okay, let's use equation 2. Okay, let us replace this one with the definition so that we can now determine the stress in the steel, which is around 191.744 megapascal. So there you have it. The stress for the bronze is 106.1 megapascal, and the stress for steel is 191.744 megapascal.